Welcome back. After the lunch break, we have a lot of important issues to discuss and technical aspects to go over. In this session, we are going to be talking about understanding the impact of hydrogen based economy and sustainability. Now, through a series of presentations, we will have a look at the different aspects of hydrogen based energy systems, the new economy, clean energy, and the future of sustainability. So during this panel discussion, during these presentations, I'll tell you the name of our presenters. We will have Dr. Ashish Lele, Director National Chemical Laboratories, Professor G.D. Yadav, Professor Institute of Chemical Technology, Mr. Manoj Kumar Upadhyay, Deputy Advisor, Energy Vertical of NITI Aayog, and Mr. Sturle Pedersen, Chairman of the Board, Green Start Hydrogen. A warm welcome to our speakers who are on the stage now. So good to have you with us. I would request Yadav ji to please go first and start with his presentations. Professor Yadav, if you can hear me, so you can go ahead.
Yeah, I would like to share my screen.
Yes, sir. Please go ahead.
Just 1 minute. Can you see it?
Yes, sir. Your screen has come. You can go full screen and then start with your presentation.
Yeah. Is it okay?
So it's not full screen. If you could just go full screen, sir.
No, it is full screen on my this thing. I don't know. Now is it full screen? Is it full screen?
It's not full screen for me because I'm
Maybe
trying
you are
to see.
using old software. Ask others whether they can see it.
Okay, I will invite Khatriji if you can just tell us. So you can start. And
I can start, right?
yeah.
Thank you very much for inviting me. Unfortunately I am caught up with another meeting here in Coimbatore. So, but since I had promised, I thought I will give my lecture from here. So I'm going to talk about innovative technologies for net zero, and particularly the role of hydrogen in sustainability and environmental protection. Perhaps you know that in April 2021, President Joe Biden had organized this climate summit, and the emphasis was on net zero, and that was also his plank for his election to the presidency. So if you look at the historical perspective between 1750 and 2018, uh, the billion metric tons of carbon dioxide which are released, United States tops the list, followed by China, Russia, Germany, UK, Japan, and India stands at seventh. At the same time, we are a huge population. So we must also understand what are the atmospheric concentrations of CO2. In January 2020, it was 410 ppm, and within a year, it rose by 2 ppm to 412. And the Paris Agreement of 2015 says that we should restrict the temperature rise of the globe below 2 degrees, and to be specific, 1.5 degrees C. And if you see at these two graphs, which I have taken from the IPCC, it says that if there is no
Professor
technology,
Yadav, I would just like to interrupt you.
ah,
I would request you to just stop the slide share and restart the slide share once again.
okay, I'll do that. I can do that. There's no issue. Okay. No, there is some problem.
No, there's no problem. You have shared it properly.
No, okay, I'll do it again. Just 1 minute. Do you see it properly now? No, this is something else I give. Let me do it again. Okay.
That was correct. You have shared your entire screen. From the entire screen, you just select the running PPT down.
No, no. So let me do that. Actually, I was trying to do something else.
So once you click present to audience, you find two options. One is select a PDF file, or one is to
So
share.
I should present the entire screen to you. Is
Yes,
it
yes.
okay?
Do that. I'll guide you.
Okay. Now, so where is this? The screen still doesn't show that.
Just click the button present to audience.
No, no, just 1 minute. Just, now, can you see that? Now, does it see?
Yes, you are right. And from the top,
Is
on
it
the
is
top
it
you
seen
have
full
the
screen? Is it full screen now?
it is full screen. From the top you have this save, undo, and then you have the fourth button, which is to present a full screen. Can you
No,
select
no,
that?
no. But right now, is it
Full
seen as
screen.
full screen?
Yeah, full screen. You can go ahead, sir.
Okay, thank you. So I was talking about this, concentration of carbon dioxide in the atmosphere. So what is happening? Energy and environment are so intimately connected, and the energy needs of the world are increasing day by day. And obviously, the use of carbon-based fuels will continue for some time, and it will rise. So, in order to meet the requirements of the international treaties, the use of renewable resources is advanced. So, the question is biomass a, an energy source? And so, if you look at some of these cases, the carbon based economy is responsible for the global rise, the temperature rise of the globe. And we know oil and natural gas and coal, these are the major ones, and a lot of power plants are based on coal. In case of India, it's very large contribution. At the same time, these days people are talking about renewable carbon, the biomass, based economy. However, whether it is a renewable or non-renewable carbon, it always ends up as carbon dioxide, and therefore we must tackle the carbon dioxide problem. So look at the petroleum-based industry and the biomass-based industry, where we talk about carbon neutral or carbon zero industry. So it means that we have to valorize carbon dioxide, no matter what is the source. So hydrogen is the cleanest fuel, which can be produced from hydrocarbons, which is normally done by steam reforming of natural gas or from water, and it can be used to convert carbon dioxide into useful products and processes. This will include the waste biomass, including waste plastic. So my personal belief is that hydrogen will be the savior for the planet Earth. And I wrote several editorials, articles, popular articles, including research articles. So the new Trinity in our scriptures and in our religion we talk about Trinity, right? Brahma, Vishnu, Mahesh. The Christians talk about Father, Son, and the Holy Spirit. My belief is that solar energy, wind energy, and hydrogen will be the new Trinity for us as far as science is concerned. So hydrogen is going to be the savior, and that is the theme. And why hydrogen? I did not go into the details and go on singing the praise of hydrogen, but that is the cleanest fuel. So I'm going to give something and what we are doing in ICT, that we have coupled carbon solar power through molten salt, and we have this thermochemical water splitting cycle, which is copper chlorine cycle. So you produce hydrogen. That hydrogen can be used to convert carbon dioxide into alkanes and many other products. Okay, that can be used like higher hydrocarbons, ethylene, and whatnot. Or we can convert carbon dioxide into methanol, dimethyl ether, formic acid, formates, syngas, alcohols, including green ammonia, well, fuel cells, hydrogen vehicles, electricity, and the very major, industry, the steel industry, where we can talk about green steel. And in water splitting, 1 kg of hydrogen gives us 8 kg of oxygen. And in today's price of oxygen, and industrial oxygen, about 10 cents per kg. So, oxygen also becomes, so both hydrogen and oxygen could be used for conversion of biomass into useful products. This is the typical refinery. So I'm talking about use of hydrogen in this oil refinery. There are 7 different processes where hydrogen is used in refinery now also. That is cat cracking, hydrotreating, hydrocracking, catalytic reforming, and this HDS, HDN, HDO, and HDM. At the same time, hydrogen is also useful for biomass feedstock. Okay, so this is what I'm going to tell you about. So what happened, around 2020, we had carbon dioxide emissions of something like 35 gigatons. And if we really want to achieve the 1.5 degree C goal, by 2050 we have to reduce this concentration or the emissions to less than 10 gigatons per carbon, 10 gigatons of carbon dioxide. So how do we achieve that? That means we have to have, otherwise, we'll have missed the bus. So let me tell you something, why this carbon-based economy, the rise of the petroleum industry. And to put you in proper perspective, before this, the first well was drilled by Colonel Edwin Drake, okay, in 1869, people used to use whales from the sea, and the blubber of the whale was used for making oil and as a source of illumination and also soap. Okay, so that the history is very interesting, and all these processes, particularly in World War I and World War II. So if you look at this 1859, for next few years, almost 40 years, there was no use for gasoline, petrol. It was just dumped into sea or, rivers and streams or lakes. Only when in 1907, Henry Ford introduced the first automobile, gasoline or petrol was used. And during First World War, around that time, and then after the 1920s, so many different technological advances took place. And that resulted into increase in production of crude oil. And we can see that this was the history. And during Second World War, the Allied forces had better technology. Okay, they had, they were using this clays of in the alumina silica type of catalyst for cracking, and therefore the crack spread increased. So you can see the World War II, and the victory of Allied forces was because of the superior catalytic technologies which they had. And now today's context, in 1960s, they introduced the zeolite-based technologies. And so nowadays we talk about ultra-stable wire. So you see the complexity of the refinery has increased. And since all the carbon is being, used for some use, that has also led to the, the very high emissions of carbon dioxide. So what we do, the oil refinery versus the biorefinery. So you can see that we can use biomass, whether it is lignocellulose or organic waste, marine biomass, green biomass, whole crop, into fuels and energy. And so hydrogen and oxygen will play a very big role in this. So what are the technology available for hydrogen production? That has to be produced cheaply and in eco-friendly manner. Okay? And only then we can talk about the so-called net zero economy, where green hydrogen will play a very dominant role. And why hydrogen? Because hydrogen specific energy in kilojoules per gram is the highest for hydrogen. Rest of the fuels, whether it is wood, the ethanol, coal, biodiesel, all they fall much below hydrogen. So you are all aware of what is meant by green hydrogen, blue hydrogen, and gray hydrogen. The refineries use gray hydrogen, where the steam reforming of any fossil fuel, or for that matter, what is used always is natural gas. You have a generation of carbon dioxide which is let go in the atmosphere. However, in green hydrogen, you may have electrolysis of water, or for example, the thermochemical cycles where the net emission is zero. Okay. And in blue hydrogen, you have to capture that hydrogen, maybe up to 90% it can be captured and stored. So that will be again steam reforming of biomass or bio oil or biogas. Okay, that is what is blue hydrogen. So green hydrogen is the one to decarbonize the industrial processes. So if you look at the hydrogen, so we can take hydrogen for transportation or convert carbon dioxide into synthetic fuels, or you upgrade the oil and biomass. You can have, with the nitrogen separated from air, you get so-called green ammonia, and the green ammonia is talked about as a, store for energy, because that can be split catalytically and you will have hydrogen. In metal production industry, like steel industry, or chemical and allied industries, or for that matter, heat and distributed power. So hydrogen will have a very, very dominant role in future. Okay, and so it is believed, this is from the McKinsey survey, that by 2050 we'll have substantial share. In fact, this will increase by multifold, and that is what is happening. So it will be something like 10-fold increase in hydrogen demand. So this is in million metric tons, 539 metric tons. And all these sectors will be covered. So what it means, that carbon negative fuels and the net zero goal will be achieved by using hydrogen. Okay. And supposing you have the biomass, look at the biomass should not be wasted on biofuels, which is emphasis across the world. Instead, it can be used to make a variety of products, right from propandiols and butanediol, propionic acid, name it, everything. And one of the important products there is hydroxymethyl furfural. We can do many things. So what happened, we did this analysis. Last year, we published a very big paper on this energy and mass balances, for crude oil versus, biomass. So what happens? Supposing you have 1 kg of crude oil, we get 32 megajoules of fuel plus 0.2 kg of chemicals. However, if you take 1 kg of biomass, it gives us only 6 megajoules of fuel or 0.8 kg of chemicals. So which is better? Okay. So it means that we should have, converting biomass into chemicals is better than converting biomass into fuels. So even that is the case with plastic waste, whether it is PVC, PET, polyamides, rubber. When you have hydrogen there, hydrogenation reactions, what you get as off gases, whether it's HCl, ammonia, or H2S, all these technologies are well known. So we don't have to worry about that. Okay, we can certainly valorize this plastic waste. So what I'm trying to tell you that if you have the current capacity of something like 97.4 million barrels per day, this is about 215 barrels per second. So if you convert 100% biomass into fuels, it will be only $10 per barrel per second. However, if you convert that into chemicals, it will be $320 barrels per second. So obviously what it means, it is better to convert biomass into chemicals. And for fuels, you go for solar, you go for wind and geothermal and whatnot, and of course, hydrogen. And so we analyze also the data given by US Department of Energy. There are more failures with the biofuel, projects than successes. That is what also we saw. So anyway, if you look at some of these important chemicals and fuels like transportation fuel, vinyl acetate, butadiene, styrene, etc., we can see that it is better to make these chemicals from biomass. Okay, so we also looked at methane conversion processes like methane to olefins or oxidative coupling of methane. And if you plot thermal efficiency against the carbon efficiency, you can see that hydrogen has very high thermal efficiency, right? So and we are talking in India about methanol economy. So how do you make methanol? You can make methanol from carbon dioxide or any other source, for instance. But methanol economy, in the context of this net zero, even if you make methanol, you can produce a large number of chemicals. So yes, and so we have this. I wrote a very important paper which was published just last week in Green Chemistry and methanol economy. And so, yes, we can do that. And if you look at all other chemicals which can be produced, so we have C5, C6 sugars, we can produce a variety of these compounds, or cellulose or hemicellulose, for instance. And from biomass, you go to lignin part of it, and all of these are catalytic reactions. So you can have a rich catalog of chemicals from biomass, and that is what is going to happen in, after 2050 when we will not have any crude oil. So biomass, we have, we can convert into a variety of things, either use it as a combustion source, for heat or gasification, pyrolysis, liquefaction, whatever you do. So when you take biomass and the lignocellulosic part of the biomass, you do hydrolysis, maybe you use acid or alkali, or people are also have started using ionic liquids. Yes, we can convert that. And one of the important compounds is 5-hydroxymethylfurfural, 5-HMF. See how many value-added chemicals can be made from this. So this HMF can be derived from glucose, okay, or fructose for that matter. So yes, so we can do this. And so for industrial hydrogen production, you may have steam reforming of natural gas, oil and naphtha, coal gasification, water electrolysis, and others. So once again, when we have hydrogen and you take that 5-HMF, variety of chemicals can be produced. I won't go into the details of this. We can see that, or for that matter, when you have glycerol, which is almost 10%, which is coming from that biodiesel portion, right? So it can be catalytically converted into esters, ethers, epichlorohydrin, acrolein, acrylic acid, propanols, name it. So glycerol has to be valorized, only then that biodiesel can become economical. So yes, from the the biomass, we can produce variety of chemicals, including you can depolymerize, you can deoxygenate it, you can reduce it. All sorts of things can be done, including these so-called oils and fats. So oleic acid, linoleic acid, all those things, they can be very good source. And so what we see in both hemicellulose, lignin, and fats and oils, we can produce a variety of chemicals, So these are all catalytic technologies. And in the case of consumer plastics, there are 7 different types of products, right? Whether it is PET, HDPE, or all sorts of things, or polystyrene, or polyurethane, polypropylene. All these wastes can be converted into valuable chemicals. So this is so-called chemical recycling, upcycling, downcycling. These are the terms which are used these days. So we do one of the things. For example, we have chemolysis, pyrolysis, and gasification. And in chemolysis, the chemicals are used to break the bond and convert. So maybe hydrolysis, glycolysis, aminolysis, name it, or acidolysis. So hydrogenation of plastic, which can handle all these troublesome atoms like chlorine, nitrogen, oxygen, and sulfur. So you can see that these are catalytic reactions. So the dual function catalyst is used. Like there is a cracking function and there is a hydrogenation function. Since refineries are already doing it, we don't have to worry. So we can certainly use waste plastic as a source, for making all these chemicals. And the other area which I talked about is steel industry. India is the second largest producer of steel, and if I'm not mistaken, something like 120 million tons of steel will be produced by first quarter of next year. So you see that this is where you have to use hydrogen, because steel industry is highly polluting industry. So you have in the zero carbon production, for example, you take electrolysis, and over the years, by 2050, the cost of this will go down. Okay, and there are many. So what do you need? We need hydrogen storage. We need hydrogen distribution stations, and these kind of things which we are already seeing, which is happening. I'm happy to tell you that the Petroleum Ministry has appointed a committee for hydrogen, and I'm a member of that committee. Just yesterday, we had a meeting on that, and we are going to prepare a roadmap for hydrogen-based economy. Okay, so and in the other part of the story, that is the so-called blue hydrogen, we have produced large number of papers and patents, and so this is just whether it is ethanol, methanol, N-butanol, ethylene glycol, glycerol, or waste biomass, we have some of these so-called blue hydrogen technology. The story which I'm going to tell you about is the thermochemical water splitting. We had worked on sulfur iodine cycle as well as copper chlorine cycle, and we concentrated later on copper chlorine cycle. This has been supported by ONGC Energy Center. So what happens in this particular cycle, we are already coupled this with solar energy. So we can produce hydrogen at less than $1 per kg, but the capacity has to be at least 100 tons per day of hydrogen production. Otherwise, that cost can go up, anywhere between $3 and $4 per kg. So if you have a high capacity, certainly hydrogen can be produced. That is what we have shown. I'm glad to share with you that we'll be having a much bigger pilot plant with the help of ONGC in Goa. So yes, there is no carbon feedstock, water as a feedstock. And we also learn the importance of new materials, because these were required for that particular plant. So yes, if you analyze the hydrogen production technology, whether they are thermochemical, electrolytic, or photolytic, so and these days we talk about a lot about solar energy. So you have a carbon dioxide pool, you have a biomass pool, and then you convert carbon dioxide to syngas and do all sorts of things. Okay, so that is also possible. So if you do the comparison of reforming technologies, these are mature technologies, steam reforming, autothermal reforming, partial oxidation, okay, these are mature. So what we do, suppose we look at the maturity of the technology, steam reforming and partial oxidation, see, these are commercial processes, efficiency is very high, 70 to 85%. And biogas gasification, 35 to 50%. Alkaline hydrolysis, 50 to 60%. So the mature technology, a lot of work is being done, and the future technology. So what we did in the case of our production, so we said, can we compare with the published literature and all? So like steam methane reforming with carbon capture. You see the cost of the capital cost here and the hydrogen cost. This cost ranges anywhere between $1.34 to anywhere up to $10. Okay. So that is what is happening. So you can see that here it is $5, it is going up, it is $10 here. So where it is the photoelectrolysis using solar energy. We compared our process with that, and we can say very confidently, we can produce hydrogen at 90 cents per kg. So obviously, and our efficiency of the overall process is 83% plus. So it is very good. So we also do life cycle analysis of this renewable or green hydrogen. Of course, you know that the greenhouse gases in green hydrogen is 0. But if you do steam reforming of natural gas, it will be 99 kg carbon dioxide per kg of hydrogen. But if you do steam reforming of natural gas with carbon capture and storage with 90% and 56% capture, that CO2 emission will be 1 and 4 kg. And the natural gas prices from European Union, this data were taken from the International Hydrogen Council and Bloomberg New Energy Funding and European Union. So you can see that the natural gas price there is something like 26.8 US dollar per megawatt hour. And the electricity prices vary, a very wide range between 43 and 106. And the capacity cost of 730 per kilowatt. So if you see the cost of hydrogen, electrolyzers cost around 1100 US dollars per kilowatt. And they may cost something like 220 by 2040. We target something like 2030, and India is also talking about that. So the cost of carbon capture and storage increases the cost of steam reforming of natural gas. Okay, so from anywhere from 990 US dollar to something like 1850. And the low carbon fuel with fossil based hydrogen is around 2.5 to 3 US dollar in the European Union. And the Department of Energy of US says that it should be green hydrogen should cost something like 1.3 to 2.9 per kg. So target for solar electricity is to be cost competitive with the current fossil fuel system. And if the cost of the installed PV power can be reduced from the present cost about US dollar 5 per watt, okay, to about US dollar 1 per watt installed capacity, the cost of the solar electricity is predicted to reach about 0.1 per unit, okay, US dollar. So what it means that if you look at the future cost of electrolytic hydrogen, including the operation and maintenance, today in a small plant, it can go where anywhere up to 4.5 okay, dollars. So larger plant, it will be 3 or something like that. And in continuous future processes, it is predicted that it will be anywhere between 2.5 and 3. Okay, so typically about 2.5. And the refinery cost of hydrogen today, the so-called gray hydrogen, is about $2 per kg. So if we match that, then it will be very, very important. The so-called hydrogen economy will be very, very important by 2030. And the electrolysis from renewable and nuclear powers become important. Okay, so if you have a hydrogen economy, and if you bring down the cost of hydrogen to less than $2 or $2.5, that will be a very attractive proposition. So once again, I'm telling you that we could produce this hydrogen at less than $1 per kg, where we had not even accounted for the oxygen contribution in the valorization. This is just to get a feeling that yes, we can do it and India can do it. Of course. So what is going to happen in the hydrogen economy in the future? So we will have a transportation sector will be greatly affected. You will have vans and coaches and taxis and all SUVs, name it. So yes, the steel industry, ammonia, so-called green ammonia, methanol, refining, dimethyl ether. And dimethyl ether is a very good substitute for LPG and also diesel. But we don't have a policy in India. So we should have a policy. That's what we have been talking about. So yes, hydrogen economy will give us very, very important lead as far as technology development is concerned. So what is my last 2 slides? Yes, production of green hydrogen, carbon dioxide, refinery and sustainability is possible for the so-called net zero goal. And hydrogen will also play an important role in circular economy. Okay, so we, as I said, including the waste plastic. So yes, we can have hydrogen as an important partner in the circular economy. So what is the way forward? India can do it. So green hydrogen will be the savior of the world. Hydrogen economy can be elegantly intertwined to make many chemicals from waste carbon sources, including C1 off gases and biomass. Government of India should adopt the hydrogen economy to meet the demands of the Paris Agreement and ICT OEC, because my work was supported by ONGC Energy Center. They have been supporting since 2007. It is very promising technology. This can be one of the many other technologies. We have already transferred DME technology to Godavari biorefineries. They have, 200 tons of carbon dioxide coming up from one of the fermenters. So we are trying to go on a much larger scale. So that is the only way we can do it, and India can do it, we can make it. With this, I conclude my lecture. Thank you so much for listening to me very patiently. I'm sorry I had to rush, but thank you so much once again.
Thank you so much, Professor Yadav, for your presentation. Very optimistic, and let's hope the hydrogen economy will fall in place for our country soon enough. Thank you so much for your presentation. I will now request Dr. Ashish Lele, Director, National Chemical Laboratory, to please address the audience.
Yeah, you have to excuse me because I have got another meeting going on. Okay, thank you so much.
Sure, Professor Yadav.
Yes, can you see me, Anisha?
Yes, I can see you, Dr. Lele.
All right, I will share my presentation. Do let me know when you see the screen.
Yes, we can see your screen. You can go full screen and start.
Do you see my full screen?
It's not full screen yet. We can see your screen, we can hear you, but it's not full screen yet.
Okay. Let me try to share the screen, which is already screen. Hold on.
Yeah.
Is that now visible? Hello?
Right. Dr. Lele, I can see your screen.
Okay.
But before you begin, I just wanted to check with Mr. Patterson. Sir, do you have a flight to catch? I believe you're in the airport lounge. Do you have a time constraint? Would you like to present first?
No, that's fine. Please.
All right. Dr. Lele, please go ahead. We can see your screen and we can hear you clearly.
Okay, how much time are you going to give me so that I will make sure that I don't delay Peter?
No, he'll wait, sir. Please go ahead with your presentation.
Okay, great. Thank you so much. I'm going to talk about how we could leverage R&D for building green hydrogen economy for an Atmanirbhar Bharat. Professor Yadav has very nicely covered the importance of hydrogen, so I will not spend too much time on the importance of hydrogen. And since I come from an R&D institute, I believe it would be good for me to talk about how R&D can be used to build a hydrogen economy in India. And I believe that it's an important topic for building this kind of new energy transition in the country. So just to give you a very brief background about why we are talking about hydrogen, I think in the last few months we have seen enormous push from the global community on climate change. The first thing that came up was the IPCC report, the sixth assessment report, which was so beautiful and had a large number of wonderfully created graphs, charts from extremely sophisticated models that looked at different scenarios for greenhouse gas emissions and the effect of these scenarios on global warming and different other parameters for global warming. The most important thing that the report said this time was that unambiguously anthropogenic emissions, that is human emissions, have been very, very important factor for the global warming. I think this was the first time that the IPCC report claimed this to be an unambiguous contribution. The second thing that happened very importantly is that the Nobel Committee emphatically awarded the Nobel Prize to two leading scientists whose wonderful science actually laid the foundations for all these sophisticated models that are used today for how the for how CO2 emissions can affect the climate and the weather. So the two gentlemen shown here are the Nobel awardees for this year. So these two very important events, the IPCC report and the Nobel Prizes, had sort of set the tone in the last few months for the seriousness of global warming and climate change. This all sort of the icing on the cake came when the COP26 happened in Glasgow recently, and very nicely our honorable PM sort of led the charge on climate action by announcing the 5 important steps that India will take. This was the India's national statement, three of which are really important, particularly in the from the point of view of hydrogen. One was a 500 gigawatt commitment for renewable energy installed capacity by 2030, 50% contribution of renewable energy to the entire energy mix by 2030, and something that was unexpected from India, the announcement of achieving net zero by 2070. What this means is that we have to transit from today where we are, which is more than 90% of our energy demand met by fossil fuels. We have to transit to a situation where 50% comes from renewable energy. Uh, and that's certainly easier said than done. Uh, but what it also means is that there are some sectors which may be difficult to completely decarbonize by using only renewable electricity per se. These are sectors where hydrogen is necessarily required as a molecule and as a reactant molecule. For example, in the refining sector, the cement sector, the iron and steel sector, and other such sectors where hydrogen is used as a molecule for a number of chemical reactions. The other sector being heavy transportation, heavy duty transportation, which in India is a huge segment and contributes to more than 10-12% of the emissions from the country, and these are all decentralized emissions. So some of these sectors totally can contribute to more than 30% of total India's emissions, which, as Professor Yadav also talked about the numbers for about 3.6 gigatons of CO2 equivalent emissions. So more than 30% of that is a very large number. And these emissions from industry, heavy transportation, and sectors like those are difficult to be met by purely renewable electricity. You need a different energy vector, and we believe that hydrogen is an excellent energy vector to achieve that. Uh, and this is because hydrogen is what is called a sector coupling energy vector. It can couple renewable energy that can be obtained from multiple sources, convert those electrons into gas, into hydrogen molecules, and then use that hydrogen as an energy feedstock or as a fuel, or also back to generating electricity. And therefore, this coupling between renewable electricity and hydrogen offers a way of decarbonizing some of these difficult sectors. And we believe in India that hydrogen could be an interesting option because it does this 9 things that I've shown on the right. Because of the abundant solar availability, water availability, once you scale up, the hydrogen production can become affordable. And because of the diverse sources from where hydrogen can be derived, we don't have to then depend on only one source or only a few countries from where energy demand can be met. So in that sense, India can really become truly Atmanirbhar in energy source, where hydrogen is coupled with renewable electricity. Interestingly, because of the abundance of, let's say, solar across India, hydrogen can be produced in a decentralized mode. The strong advances that India has made in the digital sector can couple with these decentralized production of hydrogen and therefore enable the deep decarbonization of these sectors. And this kind of opportunity enables to create a lot of entrepreneurship and ability to actually make India from a net importer of fossil energy to a net exporter of clean energy and help build India's economy, but on a clean energy platform. So these are some of the very interesting parts of hydrogen. And therefore, on the most important speech to the nation by the PM on the Independence Day this year, he made a very important and emphatic statement that hydrogen, green hydrogen in particular, can provide India a quantum jump to address the climate change. There are many opportunities for hydrogen in India. Professor Yadav touched upon some of them. we believe that in the near term, which is maybe till 2030, 2035, we can produce about 5 million tons of green hydrogen, which will amount to about 10% of the renewable energy capacity, which I talked about, 500 gigawatts. It can be used to initially create demand by replacing some of the gray hydrogen in refining and fertilizer sector to green hydrogen. And there are phased already thoughts available now and put forth by the MNRE on how this phasing should happen. And also that green hydrogen as well as green ammonia can be produced on some of the important ports in India, particularly on the eastern coast, and then therefore enable India to actually start exporting green hydrogen and green ammonia to the existing markets in the Far East, such as in Japan and Korea. In the midterm, you will need a little bit of time to lay the infrastructure for supply distribution of hydrogen, creating refueling stations along important corridors where freight transportation happens, such as the Mumbai-Delhi corridor or the Mumbai-Chennai corridor. And if that, as and when that infrastructure builds up, which may take another 10, 15 years, you can scale up the hydrogen production to meet about 10 to 12 million tons of green hydrogen demand that will be created by these new sectors. And that will be about 20% of the renewable energy capacity. We need to shift our heavy transportation from diesel-based vehicles to hydrogen-based vehicles, and they could be either hydrogen-based internal combustion engines or hydrogen-based fuel cells. There's a lot of backup power generators that we use today. They're ubiquitous across India, and as the economies of scale set in and sources like fuel cells become economical, we could actually shift from those decentralized emissions produced from the backup power generators to clean sources using hydrogen. In the long term, some of the difficult sectors such as steel, cement, those can shift to green using large amounts of hydrogen. Grid balancing could also be done using hydrogen when it is produced at scale. And I personally believe that by 2070, for example, Indian economy is certainly going to expand very significantly, and there are any numbers that are quoted in the literature. I believe that it could at least become the size of European Union, which today is maybe 25 trillion, may become 30, 35 trillion by 2050. At least Indian economy will reach that point of time. And if you look at Europe's projections for hydrogen by 2050, they're talking of 100 million tons of hydrogen. And so, in India, we should set that ambition to reach at least 70, 80 million tons of hydrogen by 2050, 2060, whatever number you want to put. But I think we have to have that ambition because it makes imminent sense for India to get into hydrogen. While this is being thought through in the government circles, the private industry in India is also betting on hydrogen. And you've all heard of very large commitments made by Reliance Industries, by Adani, to invest very significant amounts of funds in renewable energy, of which hydrogen becomes an integral part of that value chain. So I think there is a euphoria in India, both from public sector and private sector, recognizing that hydrogen is an important energy vector for India, and therefore making serious investments in this field. This is happening, of course, globally as well. According to the latest Hydrogen Council report, there are more than 500 large hydrogen projects across the value chain, that is from production, transport, distribution, supply and distribution to usage. There are more than 500 large projects that have been announced, and you can see that they are spread across all the geographies, particularly heavily concentrated in Europe and in China, Japan, Korea, of course in Australia as well. So a lot of excitement about hydrogen. The hope is that by 2050, the hydrogen production could reach more than 600 million tons. And if that happens, all of that being green or low carbon hydrogen would cause 80 gigatons of cumulative abatement of CO2. And country-wise, as I said, Europe is looking at about 95 to 100 million tons of green hydrogen production by 2050. China is looking even more than that. On the other side, the technologies for hydrogen across the value chain have become extremely mature. We have fuel cells that are very compact and have extremely high power density. People are talking of 5 kilowatt per liter uh, power density emerging from fuel cells. So extremely powerful, uh, power generating devices which have been scaled up. Electrolyzer facilities are being scaled up. We have at least one factory today in the world that is set up to produce gigawatt scale electrolyzers. There are multiple companies in the world that are producing high pressure hydrogen cylinders. So everything is being scaled up, uh, which means that the technologies are very mature and the economies of scale are coming in. And a variety of different applications are emerging. They've been tested in various geographies, and some of them are shown pictorially at the bottom of the slide. So, in general, from every side, this time we believe that the hype in hydrogen is for real, and this is very exciting. So, in this context, in India, what should be the role of our R&D in hydrogen? I give here 10 points which I believe are points where R&D in India can play an important role. And starting from not just make in India, but innovate in India, focus on core technologies that are required to make various parts of the hydrogen value chain, whether it is membranes, catalysts, carbon fibers, epoxy resins, and whatnot. So focus on those core technologies, create high value IP so that our technologies remain globally competitive, and also help both the corporate and the government sectors to build the strategic roadmaps. Professor Yadav talked about he helping the Ministry of Petroleum to build a roadmap for hydrogen. So I think R&D can play a very, very big role in that part. So I won't go through the list, but I believe things even like helping build standards, creating testing facilities. And I know Norway, and I think Sturle will talk more about it, is already setting up excellent COEs in India, where things like these, skill development, testing facilities, can all be created. And there's a lot of learnings from outside which countries like Norway want to bring to India. And I think we should make use of those opportunities so that we don't reinvent the wheel. We can leapfrog from those learnings. Where I come from, which is CSIR, we have been looking at hydrogen since 2002. And we started a program called a special purpose vehicle called NMITLI, which basically looks at uh, translating science into technology early on, where there is very low market uncertainty and where the technology readiness levels are very low. So we positioned this special purpose vehicle in CSIR in that quarter where market certainty is low and technology readiness is low, so that we could get in this game early on and start looking at these kinds of new technologies. So we looked at hydrogen back in 2002. We developed these programs along with industry participations, and we looked at a number of things. We started with methanol reforming. We learned how to do that. We started with PEM fuel cells, electrolyzers, biohydrogen, solid oxide fuel cells, and so on and so forth. We've made about 100 crore investments in these R&D so far, which, for India, we may think these are large investments, but if you look at global investments, these are really very frugal investments, right? And that is interesting in India because sometimes we learn how to innovate and valorize on these frugal investments. So over these investments, what we've achieved so far are we have now technologies indigenously developed to make good testing facilities so that when technologies come to us for validation, certification, we have testing platforms where we can do this. We have built India's first indigenous fuel cell car, where the entire balance of plant has been integrated into the car. And this technology is now being scaled up to the first bus. We also built a backup power unit of 2.5 kilowatts for supporting towers, the telecom towers in India. We have small electrolyzers which we have installed at various places, including outside in Oman. We have a small reactor producing about 10 kgs of steel based on hydrogen plasma, so absolutely zero emissions. And we have also been working very closely with the coal ministry to convert coal into syngas. Right? Syngas, of course, can be converted into hydrogen, but a better utilization of that is to get into liquid fuels, as also mentioned by Professor Yadav. While doing this, we've created a lot of IP around core materials, core technologies, and we have also developed a few vendors, for example, vendors for manufacturing plates that are used in fuel cells and electrolyzers, porous carbon paper layers, catalyst coated membranes, and so on. So we've looked at science, we've looked at proof of concept development of technologies, and we have also along the way developed a few vendors. And it's time to now really scale up. And so what we are doing at CSIR is putting together a mission program. There are 19 laboratories in CSIR which are engaged in the three parts of the hydrogen value chain: generation, storage, and utilization. And we're bringing all of those programs under a hydrogen mission of CSIR. We are also tying up with DST, who has its own programs on hydrogen. The Hyderabad lab, for example, has done some very pioneering work in hydrogen, in fuel cells and electrolyzers. There are two centers of excellence set up by the DST at IIT Bombay and NFTDC, which are looking at hydrogen storage, which is a very, very important area in the hydrogen value chain. So what we are proposing now is a joint DST CSR technology mission, whose goals will be aligned with the aspirational goals that were articulated very nicely by our Science and Technology Minister, and he called it the Hydrogen 212. I will not elaborate on it for lack of time. We believe this joint technology mission is very deeply aligned with the National Hydrogen Energy Mission of the MNRE, and we will in fact help in operationalizing the National Hydrogen Energy Mission in multiple ways. The ones that I've listed in red, for example, are ways where we can come in a big way to support the National Hydrogen Mission of India. So I will skip some of these slides, and what we want to do here is, in the mission mode program, these are mission mode programs where we want to have very sharp focus on delivery, very sharp time-bound way of delivery, and to be done in partnership with the private companies. So this will be in a PPP mode. Our focus will be on first in the green hydrogen production, focusing on electrolysis. And within electrolysis, we will also focus on all parts that make the electrolyzer. There is a catalyst, the membranes, the bipolar plates, the stacks, balance of plant, power electronics, and all that. We will also look at the other two technologies, the biohydrogen and pyrolysis, but these are at a lower TRL levels. So these are more a little bit midterm in nature. We are now looking at, in the mission mode, the compressed gas hydrogen for storage and distribution. And here the focus is going to be on carbon fiber, on recyclable epoxy resins, on making the cylinders and the balance of plant that are required with these cylinders, which are the valves and the safety sensors and so on. So these are all to be done in mission mode along with industry partners. Similarly, on a little longer term, we will be looking at metal hydrides and liquid organic hydrogen carriers, but not the same that are existing today globally. These will be different types of hydrides and LOHCs, which will hopefully remove or overcome some of the problems that exist today. On the utilization side, we are already focusing, as I said, on bus, the heavy-duty commercial vehicles. We are already focusing on stationary, like power backup applications, and we are already focusing on steel. And there we will again dive deep into focusing on the core technologies that make the fuel cells or the reactors for these downstream applications. And there's a whole list of fundamental research that we will be aiming at. And so these will be little longer term research, which will be done in coordination with Indian academia. And the idea is to stay ahead of competition, create IP, and use some of these technologies to upgrade, this science to upgrade our technologies. And we hope that we will be able to get sufficient funding from the government to support these high-end research, and also be able to therefore attract India's best talent anywhere in the world to work with us in these domains. Uh, while doing this, we will be developing a huge amount of competencies. Many of them exist today, and we are going to use them to create coursework and training programs, including hands-on training programs, where we will, help build the skills from very high end to more technical stuff. So these will be very focused training programs and coursework. And we'll also be creating several facilities to help us look at things like purity of hydrogen, development of, testing of fuel cells and electrolyzers, and so on. We would love to participate in some pilot projects, again, to be done in PPP mode. And there's a lot of platforms we use for public awareness that we already have in the CSI system. So at the end, I would say that the Indian R&D institutions and the academia, we are reasonably geared up to play an important role in building the hydrogen economy in India. And we must leverage this competency that exists to develop world-class technologies, do some strategic planning for important programs in the hydrogen mission, formulate standards and code, create important facilities, and even participate in important pilots that are going to happen across the country. So I think R&D has a very important role to play as India builds hydrogen economy. So with that, I will end here, and happy to answer any questions now or later. Anisha, over to you.
Thank you so much, Dr. Lele, for your presentation. Please do stay with us. Questions haven't come in so far. And I would request all the participants, if you have any questions, to go ahead and put them in the Q&A box. I would now like to request Mrs. Sturle Persson, Chairman on Board, Green Star Hydrogen, to please address the audience.
Thank you very much for the invitation to participate in this discussion about factors that has an impact on the hydrogen economy and sustainability. I'm very pleased to join this panel discussion, and it's been a quite impressive presentation by the two other panel participants, Dr. Lele and Dr. Yadav, which have done an excellent job in giving it the hydrogen economy in a good context. So what I will do is, first of all, I would run through a few of the points that has been touched upon a little bit earlier in the presentations, but focusing more upon what we need to do to make sure that India is also doing what is needed to be able to fulfill the climate commitments that they have made.
Right. Mr. Patterson, I request you to please turn your camera on so that we can see you.
Sorry. Okay.
Yeah, please go ahead.
So hydrogen as a clean, reliable, and potential sustainable energy carrier has, as we know, have heard today from Dr. Lele and Dr. Yadav, attracted a growing interest for promoting the sustainable development of both industries and society worldwide. Hydrogen is a rising enabler for a transition toward a low carbon economy based on renewable energy sources. Hydrogen is considered by many, as we have heard also today, as a rescuer transforming the energy system. A hydrogen economy builds on hydrogen and electricity as energy carriers. For hydrogen and developed chemicals derived from hydrogen, the term energy carrier is widely used and refers to an energy-rich substance that facilitates the transportation and the storage of energy with the intention of using it at a distance in time or space from the primary production site. The green transition in hydrogen production brings about lower GHG emission, but also further advantages. The value offered by the power to X pathway encompassing renewable energy time shifts, demand load shifting and electricity arbitrage, avoidance of renewable energy, curtailment, and ancillary services and frequency control, and also not to forget seasonal storage. For instance, storage is mainly motivated by the short-term search for load stabilization and by the need to overcome long distance in power transmission in combination with, for instance, pumped hydro storage. Green hydrogen production do indeed promise to foster the integration of renewable energy system in the electricity sector, thereby enhancing the credibility of a 100% renewable scenario. Green hydrogen marks a shift to a new technology path with a centralized generation concept based on a large-scale electrolyzer feed through electricity from the grid, or a move toward a new technology model centered on distributed generation and in energy prosumers based upon industrial cluster models, which has also been touched upon earlier by Dr. Lele. Distributed generation matches better than the traditional centralized generation model, with coordination mechanisms characterized by decentralized interaction and a limited scope of control due to the small scale and the modularity. This could improve the performance of the critical functions such as load balancing and frequency control. The storage possibilities allowed for a green hydrogen would allow grid operators and utilities to delay the installation of extra generation and transmission capacity for grid stabilization. However, we see that hydrogen production in areas with high insulation exploits economy of scales, but leads to larger storage and transport demands and associated issues. And this is an area where I think the research centers in India and in the world need to look into, because this is where the cost is going to be high if we cannot get it resolved. In economies of scope, a better local fit might lead to overall good system efficiency, and economies of number could be possible when making use of its standardized modules produced in larger amounts for chemical process in general. Hydrogen is also discussed for replacing coke as a reducing agent in iron production to lower greenhouse gas emissions, and for replacing fossil fuels as a feedstock in the chemical industry. But we also need to look at the safety aspects and risk within the hydrogen value chain. An accident can have a major negative impact on the speed of the transition and the journey we are embarked on. And it can even hold the process if you have an accident without making sure that the public and people understand the technology and the risk involved with establishing a new infrastructure for the hydrogen economy. Hydrogen is an energy carrier, and the issue of how the hydrogen is produced and how the energy system around hydrogen is built are crucial. The current debate goes beyond energy supply for power and heat and a driving force in the transport sector, as we have heard, but also includes the process industry such as iron, steel, and cement, and the chemical industry, which we have been told earlier today by the other speakers. Hydrogen is a cornerstone for deep decarbonization in the energy sector, allowing for the integration of intermittent renewable energy sources by providing a massive long-term energy storage service. In sectors currently relying on fossil fuel-based carbon, such as the organic chemical industry, hydrogen enables a replacement of fossil fuel-based carbon by other carbon sources, such as captured CO2. Biomass has also been mentioned here, and recycled plastic waste, which is also another thing that Dr. Yabda mentioned. The transition to a renewable, sustainable-based hydrogen economy challenge fossil fuel-based business models and countries whose economies rely on these. And it also opens new and fosters already existing business opportunities in the renewable sustainable sector. In the area of hydrogen production, storage, and consumption, in the provision of non-fossil fuel-based carbon sources, such as carbon capture and the use and the producers of equipment in these fields that are currently seeing a steep demand for its technology and know-how. I will argue that in the new role, hydrogen is a game changer and review the policy framework for hydrogen economy with respect to the prospects of success and to its role in supporting to reach India's sustainable growth goals will be very important. And I also support Dr. Lele's view that the research and development centers in India can play an important role, but also to capitalize on the lessons learned from other pilot projects around the globe would be very important to make sure that we're keeping up the speed in this transition. A hydrogen economy provides a cross-sectorial perspective for a clean and affordable energy supply and deep decarbonization in the process industry. The possibility to store hydrogen or byproducts thereof represent a game changer for the integration of high renewable sustainability shares with positive effects on the some sustainable development goals, which will reduce the greenhouse gases and air pollutants emission. However, green hydrogen needs an appropriate policy to reach a level of playing field that takes account for at least 3 issues. The first one is centralized and distributed green hydrogen concepts will involve significant trade-offs in terms of economy of scale and the scope and the storage and the transportation needs, and also the energy knowledge. Policymakers must assess which concept solves the trade-offs in ways that are most suitable for sustainable development growth goals. The other one is selecting the concept would require a comprehensive assessment of how green hydrogen impacts not only the clean and affordable energy, but also sustainable development goals. Economic growth opportunities for India, well endowed with renewable resources, may be at stake if geopolitical power, financial resources, and technology are unevenly distributed or not secured. That's why it is important that India develops its industry and secure the core competence in all the aspects of the hydrogen value chain. The most recent cost projections on green hydrogen should be stimulating and encouraging for all of us to move fast ahead. Deep uncertainty on the pace at which the world is reaching climate tipping point and the macroeconomic consequences of the COVID makes it difficult to cost of capital. However, a global coordinated initiative needs to be worked out. Strategic alliances and cooperation will be essential to secure funding and success. Falling cost for renewable energy systems and improving electrolyzer technologies could make green hydrogen cost competitive by 2030. But even today, we know that in many areas, we have cost competitive solutions for hydrogen if we don't take into account storage and transportation. That is why we see that a lot of the pilot projects in Europe and other places in the world is developed around off-grid solutions and so-called industrial clusters. So for this to happen, innovation in hydrogen industry is strictly required. And that's why funding for the research institutes in India must happen if India is going to achieve their goals. A policy implementation which appears certain and credible is important for the stakeholders also to invest in low carbon, long-lived capital stocks to avoid sunk cost. The hydrogen economy is both a chance for greater public acceptance and for immense funding. but will also pose a risk if research not directly aligned with the hydrogen economy and receives less funding in the future because we think that the job is already done. As it has been outlined by Dr. Lele, there is many areas where we need to make improvement to increase the efficiency and also avoid the efficiency losses that we have by converting hydrogen back to electricity. With increasing use of hydrogen and technical advances, the cost of production, distribution, and product manufacturing will become increasingly affordable. By continuing to build partnership between businesses, government, and universities, which has been highlighted by Dr. Lele, and a non-profit organization, hydrogen will be the foundation of a global sustainable energy economy. Thank you very much for your attention.
Thank you so much, Mr. Patterson, for your presentation. We have few questions that have come up, and I request Dr. Lele also to be around to answer these questions. So Prakash Thanki, Assistant Manager, 20 Microns, has a question. His question is, what kind of metal hydride potential on hydrogen production and importance in transportation? What is the kind of metal hydride potential on hydrogen production and importance in transportation? Mr. Patterson, would you like to take this?
Well, I think it's still at the early stage. I think perhaps Dr. Lele is better in position to say what is the latest that has happened in the hybrid metal research. But certainly there is high hopes that the metal hybrid can be a way of transporting larger quantities of hydrogen. But we know that there is some tricky aspects of it. Either the combination is too strong, and it creates then a lot of energy to the how can I say separate it when you come to the consumption point. And if it's too weak, then it's unstable. So there is again just kind of underscoring the need for further research and development in this area. But it's very promising. But today, I think that the best way of transporting it is to look at ways to use the already set of infrastructure, which blending hydrogen with natural gas, even with methane. I have seen that there is research going on where it is easier to separate it from hydrogen. But we need to use the existing infrastructure as long as we can. The cost for this is 1/10 of what it is to build a new infrastructure, and to plan and to set up a new infrastructure for pipelines, for instance, which also Dr. Lele mentioned, will take 10 to 15 years. So if we are going to be successful and implement this in a short term, we need to look at what we have and how we can utilize that. The cost is also less.
All right. Dr. Lele, would you also like to come in here and
Sure.
begin?
Yeah, sure, Anisha. Yeah, so I do echo Sturle's response. I'd just like to add a few things. One is that today's best metal hydrides, there are two types you have. One is where it will react with hydrogen, form a metal hydride, and then, as Sturle also said, requires a secondary reaction to extract the hydrogen out of it. In the process, it produces another compound which will have to be recycled. So this is, you make metal hydride at one end, extract hydrogen at another end where you use it, and then recycle the compound back to formation of metal hydride. So this will be a material that goes around from the production facility, the metal hydride production facility, to the hydrogen extraction facility. There is a problem with that, two problems with it. One is the amount of hydrogen per kg that you can store in the metal hydride is still not close to what you could do in compressed gas. Second is, as Turle said, you need to input energy to extract the hydrogen out, and that is a cost disadvantage. However, there is a lot of innovation happening on a new class of metal hydrides called the high entropy alloys, and there uh, the storage potential is low. However, there are no reactions happening. It's a physical absorption of hydrogen into metal hydrides and a physical release of hydrogen from the metal hydride. So those are interesting options to look at. So to cut a long story short, this is an interesting field evolving. Uh, it will right now it is not it cannot compete with compressed hydrogen gas. I would not use it for transportation application because it would carry a lot of dead weight of the metal hydride. But it might be an interesting option for stationary storage of hydrogen. So not so much for transportation, but stationary could be interesting.
All right. There is another question which is coming in, and I just okay. It's from Prakash again. What is your guidance on magnesium hydride as it is as is release H2 while add in water and make magnesium hydroxide which can be used? Ashish, Dr. Lele, would you like to take this? What's
Yeah,
your
yeah,
guidance on magnesium hydride?
yeah. So that was the point that we were making, both Sturle and I, that you magnesium hydride can store enough hydrogen, reasonable quantities, but if you want to extract hydrogen from it, typically you would react it with water and get magnesium hydroxide out of it. Now, magnesium hydroxide potentially can be sold as a byproduct as well, but I don't think that's a very good option. You would rather convert the hydroxide back into hydride, so that you can recycle the magnesium around. The reason I'm say that is where the hydrogen is extracted out, where you produce the magnesium hydroxide, you will need a separate supply chain to take the magnesium hydroxide to sell it into to a customer who would buy the magnesium hydroxide. Uh, and magnesium hydroxide has high value pharmaceutical usage and so on, but the supply chain will have a cost of its own, uh, and the volumes that you will produce may not be enough to meet the cost of the supply chain. So there are interesting technologies around magnesium hydride, like the Fraunhofer has the magnesium hydride paste, for example. Technically, it's possible. Whether it is viable remains to be seen.
Hmm. Right. Um, so those are the questions that we've got in, and we've got some comments from um, the audience that they have really enjoyed the presentations made by both of you, Dr. Lele and Sule Patterson. They've really enjoyed your presentation a lot. And we thank you from the bottom of our heart for coming here and sparing the time and sharing your expertise with the audience. They're in the thick of things, doing operations daily. But new ideas can come on these platforms and new ideas can be developed on. And the Gasification Year Conference is giving a platform for a number of these ideas to come in. I'm sure everybody has benefited immensely from your presentations. Thank you both for joining us, and we'd like to thank Professor Yadav as well for his presentation. So now what we're going to do is we're going to wrap up this session, and we'll slip into a networking tea break. We'll be back at 4:30, and we'll talk about hydrogen production techniques made in India, what innovations are possible in India. So do join us again, and we'll see you at 4:30.
Thank you very much, Anisha. Thanks a lot.
Thank you very much.
Thank you.